Hello, Math 30-1. We are nearing the end of our travels through transformations. Um, and we have with us today a transformation called stretches about the x and y axes, the A transformation. So our journey so far has talked about y equals f at x. And when we transform f at x, we can have all sorts of things. We could have y equals a times f at b x minus h plus k. And with that, all the transformations are included. So what we've done so far, to recap, we have looked at h and k, and we have also looked at our reflections. We're now going to deal with a in this first part for sure. Okay, so when we deal with a, what's going to happen? I would like you to complete the investigation, and then when it's time, please come back and look at this. But do part 1 and part 2, and then come back and see what kind of conclusions we can come up with. In part 1, it says write an equation 3f at x. Well, I know what that looks like. If I'm supposed to write 3 times f at x, that would simply mean putting a 3 on the outside of that square root. Oops. So when I do that, that would be 3 square root 4 minus x squared. I go to my graphing calculator and I sketch the graph of 3f at x. And lo and behold, when I do that, I get a picture that looks like this, right? Use your graphing calculator and don't trust me, so I did that. Check. Describe how the number 3 and 3f at x affects the general sketch. Well, you can discuss that. I think it looks to me like if you were to grab, I'm just going to show this, if you were to grab this point right here, it seems to me that if you stretch it and you have this gentleman right here grab on and pull it up, seems to me that it has vertically, seems to me that it has vertically stretched about the x-axis by a factor of 3. Now what do you say I mean by that? Well, what I'm saying is that it looks like these 2 points are anchored in, and it looks to me like this guy up here has grabbed on and he's pulled this up like I showed, and this used to be a point of 0 and 2, and now that point up here is now a point of 0 and 6. It's 3 times taller than it used to be. The x-intercepts of the graph, well, they stayed the same. They are still at, you might call them no change, or they're invariant. How did that affect? Well, there was no change in the x-intercept. And the y-intercept of this graph was clearly, again, multiplied by 3. It was 3 times bigger than it used to be, right? If we continue on and write the equation for 1/2 f at x, right? So the same function, well, if I do 1/2 f at x, and I go back to, I got to remember what the equation was, I go back to the original one, y equals 1/2 the square root of, what was it, square root of 4 minus x squared. Then I type that in my graphing calculator. Well, I go and do that, and lo and behold, what I end up seeing is these critical points. Again, I describe how half affects it. Well, it seems like f at x has been vertically stretched by a factor of 1/2. In other words, the graph, the blue graph, is 1/2 the height. So it's almost like this guy is standing above this thing, puts his hands on the original graph and presses down, so it's now only half as tall as it used to be. How did it affect How did this blue graph affect the x-intercepts? Well, it didn't. There was no change. You say. What about the y-intercept? Well, the y-intercept was now half or multiplied by a half. So based on what we learned in parts 1 and 2, complete this and then come back and see whether you agree with Mr. K. Complete the following. So if I compare the graph of f at x with the graph of af at x, it results in a vertical stretch about the x-axis by a factor of a, whatever the a value is that affects it. If, oh, note, stop sign. How you see that a value can differ. So for example, when you see the a value right here, I'm just going to go back up to the top. So we put it right at the heading of our notes. If you see the a value right here, that's normally where you see it, outside of the function. But you could also rewrite it, and we always have to see things, if you divide both sides by a. So in other words, if you had y equals a f at x, you could say, well, I could divide both sides by a, and as a result, you might also see this function as 1 over a y equals f at x. And so the reason that they mention that is when we talk about replacements for y, it can be worded in a reciprocal way because that's how it'll end up looking at when you put it in. So a replacement of 1 over y, or sorry, 1 over ay, when you put it into the function and you solve it for y, ends up looking like this. So take the time to make sure that makes sense, and we can talk about that in class after, okay? Continue on with the next page. All right, so now you want to continue, and now they're comparing the graphs, and just so we're clear, what's going on from here to here? Well, in terms of replacement, x is now replaced with bx. We've done all kinds of things where x is replaced before. We talked about x is replaced with x minus 3 and things like that. Well, what happens when x is replaced with bx? What happens to the graph? So here, I want you to write the equation for x being replaced with 4x, and then in the 1 down here, x is now replaced with 1/3 x. And what does that do to the graph? All right, so come back after you've completed parts 1 and 2 for the b transformation. So what we should have found as we did the equation was we said, oh, okay, I substitute 4x in for x, I get y equals 4 minus 4x squared, which becomes square root 4 minus 16x squared. In the next statement, it asks me to use my graphing calculator. When I use my graphing calculator, I notice that, this point didn't seem to change. But now when I look really close, it seems like the point is right here. It's not, smartboard's being not so smart right now, but that gives you an idea. You'd be a little more accurate. And that's my general sketch. It doesn't seem to be nearly as wide. Generally, what seems to be happening is it's actually 1/4 the width it used to be. It used to be all the way out here at 2, but now it's actually only at like a half when you look. When we look at the x-intercepts, they seem to be multiplied by 1/4. When you look closely, they go from being plus or minus 2 to being plus or minus 0.5. That's 1/4 of what they used to be. So this is now, and this was before. Okay, plus or minus 2 to plus or minus 5. What about the y-intercept? Well, there wasn't any change. The y-intercept still stayed up at 2. I wonder what this transformation is about. You continue your work with this one, and when you did this one, you are going to see, well, if I put in a 1/3 x, that will actually be y equals the square root of 4 minus 1/3 x squared, which then would become y equals the square root of 4 minus 1/9 x squared. When I graph that, I notice that This point doesn't change, but now my curve now looks like that. Oopsie, right there is where I wanted to go. So those are my endpoints, plus and minus 6. So what does that seem to do? Well, it seems like it horizontally stretches f at x by a factor of 3 about the y-axis. What are the x-intercepts? Well, before they were plus or minus 2, now they're plus or minus 6. Therefore, they have been multiplied by 3. What about the y-intercept? No change. So what are the conclusions that we make as a result of part 2? Well, compared to the graph of f at x, the graph of b at x results in a horizontal stretch about the y-axis by a factor of 1 over b. So in other words, if you see 1/2, it really means there's a horizontal stretch by a factor of 2. And if you see 2, it really means it's a horizontal stretch by a factor of 1/2. What you see is the reciprocal of what happens. And notice in terms of replacement, x gets replaced with bx in this scenario. Continue your work on the next page. Okay, you guys, so this is about you playing with your graphing calculator and trying to imagine. So as you're doing this, what I want you to do, rather than just watch Mr. K do this, I really want you to use your graphing calculator and start kind of seeing what might happen. So when you see this based on what you saw, maybe it's 100% clear and you go, okay, well, if that's the graph and that graph is given to you in the picture, right? You could graph that on your calculator, but based on the fact that they're asking you to talk about minus 3f at x, what might that do to the graph and why? So what do we see as you put the graphing calculator together with this transformation? So a minus 3 on the outside is minus 3f at x. So if I slam that minus 3 to the whole function, I should get minus 3x cubed plus 6x squared minus 15 and minus 18. When I graph it, what do I see? And how do I describe it? Well, I get that over there, the blue graph. And how does that compare to what it used to be? Describe what that minus 3 does. What might you say? Well, what I say it does is it's vertically stretched by a factor of 3, and it's also reflected in the x-axis. What might another person say? And we'll talk about this more tomorrow, but you might also say that every y value, when you look at every point on here, the height of this right here is 8, but 8 gets multiplied by that minus 3. So in other words, minus 3 is multiplying all the y values. Every y value is multiplied by minus 3. So why does 8 go all the way down to this point here? Well, because it was multiplied by minus 3. And why does this point right here that has a y value of minus 4 all of a sudden become a y value of 12? Well, you might say, well, because minus 3 is multiplying all y values. So it's 3 times as tall and opposite to what the y values used to be, right? What are the x-intercepts? Well, they don't seem to change. They're invariant. IV stands for that word we talked about, invariant. Okay, IV, not intravenous. The y-intercept? Well, the vertical stretch was by a factor of -3, so it is obviously stretched there as well. Complete the following. Compared to the graph of y equals f at x, a graph of AF at x where a is less than 0 results in a vertical stretch about the x-axis by a factor of absolute value a together with a reflection in x. Okay, that's one way to think of it. Continue on with the next example and what's going on here. Again, play with your graphing calculator. So there's the graph provided, right? Provided to you. Now it asks you to do a transformation of minus 1/3 x. So don't look at my graph, okay? If you do the transformation of minus 1/3 x and substitute it in there, we end up with minus 1 over 27x cubed and 2/9 and so on, okay? You can read. I use my graphing calculator to graph it, and then I look back and I see how did taking x and replacing it with minus 1/3 x affect the original black graph. As I look at it, it seems to me that there must be two Math 30-1 students grabbing onto this thing and horizontally stretching it, and that's their anchor point. Like a tug of war, you might say, horizontally. They are horizontally stretching it by a factor of in this case, -3. They are horizontally stretching it by a factor of -3. In other words, xy has now mapped. Now this is a point. This is not a replacement notation. Again, another way of describing it was xy is becoming the point -3xy. Okay, that's not replacement, right? So it has been, we've been saying these words, horizontally stretched by a factor of 3 and reflected around the y-axis. So when you look back to your graph, now the up bump is on the right side, and the up bump is over here. It used to be over here. It got flipped around, and the down bump is over here, but it's also 3 times wider than it used to be. So it's horizontally stretched and reflected about the y-axis. Lastly, the x-intercepts of the graph are horizontally stretched by -3 or multiplied by -3. The y-intercept is invariant. So it appears that the graph of y equals bx, if b is less than 0, will horizontally stretch about the y-axis by a factor of the reciprocal and also reflect it in the y-axis. Okay? So on the next page, you've got a bit of a summary to complete and fill in words, and hopefully by now, and if not, you guys will ask Mr. K in class tomorrow, but hopefully now you can fill in the blanks here, and I'm just going to scan, and I would much rather you not. I'm not going to talk through this because you don't want to hear me, but you can pause it and see whether this is something you're at peace with. Okay? All right? If you're good, you're good. If you're not, ask and make peace with the math, okay? On the last page is again some more tricks with notation, right? Just be careful. Don't let them trick you with these different versions. That's part of making peace with I guess deeply understanding things rather than just sort of memorizing one version. We have to understand the different ways it can be expressed, okay? Nothing really new here, but it's something you need to highlight and make sure that the words make sense. All right, ask. So let's do some examples now and finish off, and then you can get to your assignment, okay? So example number 1. Write a replacement for doing these things, right? So for example, how would you do a horizontal stretch by a factor of 6? As soon as you see the word horizontal stretch, I hope you think about the b value. That means that x has to get replaced by 1/6 x. So y would have to equal f at 1/6 x. If you wanted to vertically stretch it by a fifth, well, that would mean you'd have to put 1/5 f at x. You'd have to have 1/5 on the outside of f at x, or you would write it as 5y equals f at x. This is the most common way, you guys, okay? If you wanted a reflection in the x-axis, that's a downshift. We know what that is. That's where positive y's become negative y, so there would be a negative on the outside, as well as a stretch about the x-axis by a factor of 3. So there's 2 things that should see in that. One of them has to be the vertical stretch, so you're going to have a 3, right? You have a 3 like this. There's a 3 there, but there's also the reflection in the x-axis, which means minus f at x, okay? a horizontal stretch about the y-axis by a factor of half, and a vertical stretch about the x-axis by a quarter. So remember, the horizontal stretch, that's the B one. That's B. The vertical stretch is A. And so B's always are weird. They're reciprocals. So when you do the B factor, the B value has to be 2 to get a half as the factor. And the A value that's beside f of x has to be a quarter. And just like I know this seems like it's working opposite, but the cool thing is if you actually put this 1/4 over here, you could also write it as 4y is equal to 1/4, oopsie, no 1/4, silly. 4y is equal to f at 2x. So when the transformation is with the variable that it affects, it actually is opposite to what you see, just like you saw with vertical and horizontal shifts, okay? Lastly, in the last page, a couple other quick examples to make sure you're clear is how does the graph of 3y compare to the graph of this? A vertical stretch by a third. And becoming clear, and again, if that bothers you, don't forget, you could have also written it like this: y equals 1/3 f of x. Okay? What happens to the graph of the function when you make these changes? Well, if you replace x with 4x, what would it look like? Well, it's going to look like this. And if it looks like that, that's a horizontal stretch by a quarter. What if you replace y with a third y? Well, let's look and see. What does that look like? Right? It looks like 1/3 y, which then becomes y equals 3 f of x. What does that do? Well, it's on the outside. That's a vertical stretch by 3, right? Well, what does it look like when you replace y with 6y and x with 1/3 x? Well, let's see. What does it look like? Well, it looks like this. What do those two parameters do? Well, they vertically stretch by 1/6, and they horizontally stretch by 3. And lastly, example 4, could we sketch the graph of y equals f at minus 2x? Well, we could. We have to do two things. Number one, we have to horizontally stretch by half about the y-axis, and then it also wants us to reflect it in the y-axis, okay, because of that negative right here, right? So that's a negative on the inside, and we know that that is replacing x with minus x, okay? So let's look and see. If we do the first one, horizontally stretch by half, so the y-intercept stays the same, and we simply, I'm going to do that in green, so we simply take this point, it doesn't change, but that point's at 4, so it'll go to 2. This is at 5, it'll go to 2.5. This point right here is at 6, it'll come across and go to 3. I've now finished this half of the graph. I'll go to the other half. That's at 4. Minus 4, it becomes minus 2, and minus 6 becomes minus 3. Yay me! I have now checked off the horizontal stretch by half about the y-axis. The only thing that I need to do now is I need to reflect it in the y-axis, and doing that is really pretty straightforward. If I had a transparency, it would be really easy. But now I'm just going to take these points and go like this. So this half of the graph, this point, that point actually goes over there. And this point actually goes 2.5. So right there, and this point at 3, I come across, and it's now going to go right there. So this part of the graph now, and now I go and finish this other part off, and this point now goes here and 3. So now it becomes and we are done. Okay, we have now done, oops, I should check this off. We've now done part 2. So this blue graph, if you were to kind of keep track, this green graph was The green one was y equals f at 2x. I took care of only the horizontal shift, and by doing the blue graph, I took care of both. F at minus 2x. All right. Please complete this, or please come to class next day with any of your questions and ponderings. Well done, Math 30-1. This will be enough. Don't try and go on and do the next lesson. Let's make peace with lesson 5.